Please go ahead. We cannot hear you, Geraldo. No, we cannot still hear you. It was working. I'm not sure what happened.
Can you hear me now?
Now we can hear you.
Okay, is the audio okay?
Yes.
Perfect. Okay. I think my small microphone just died. So welcome everyone for my to my talk about MIMDRAM. I'm not going to read again, the title is quite mouthful, but this work was presented this year in HPC. So again, as a brief self-introduction, I'm Geraldo, I'm a PhD student here in the research group, Safari Research Group at ETH Zürich. So I'm going to be on the job market for industry positions. I'm going to defend my PhD in the beginning of next year. And if you want to reach me, feel free to contact me via email. And I do research mostly on computer architecture, computer systems, and hardware security. So without further ado, I'm going to give a brief introduction of what this presentation is going to be about. So the problem that we're trying to solve in this work is that there is a particular class of processing memory architectures, which are called Processing-Using-DRAM architectures, that can implement bulk bitwise operations by operating DRAM cells in the analog frequency domain. However, those process-using DRAM architectures suffers from three main issues that we identify in this paper caused by DRAM's large and rigid extragranularity. So the first one is the underutilization due to the variation in the amount of data parallelism within and across different applications. Limited computing support due to a lack of interconnects, reducing the computation pattern to be only parallel math primitives, and also challenging programming model due to a lack of compilers that can generate code for such architectures. Therefore, the goal that we have in this work is to design a flexible process-using DRAM system that can overcome these three limitations caused by DRAM's large and rigid extragranularity. So to this end, we propose MIMDRAM, which is a hardware software co-design processing using DRAM systems. So the key idea of MIMDRAM is to use this concept of fine-grained DRAM activation for processing-using DRAM operation. So we leverage this key idea in both hardware and software. So on the hardware side, we implement simple changes to the DRAM array, enabling concurrent process-using DRAM operations inside the DRAM subarray, and also low-cost interconnects that allow us to move data across different portions of the DRAM row, enable us to implement data reduction operation natively in the DRAM substrate. On the software side, we implement compiler passes and operating system support to generate and map process-using DRAM instructions transparently from the programmer from C-level code. So we extensively evaluate MIMDRAM, and we see that it can significantly outperform state-of-the-art process-using DRAM systems, high-end CPUs and GPUs in terms of energy efficiency, and also encourages small changes to the small area changes to the DRAM chip and CPU type. So the source code of MIMDRAM is available in your GitHub repository. So this is the outline for our talk, for my talk. I'm going to briefly give a background on process memory, which shouldn't be news to anyone in this meeting, and a bit more background in processing using DRAM architectures. So the concept of process memory architectures is not new. Those are architectures where computation is either near or within memory chips, so that we can mitigate data movement bottleneck suffers that current application suffers from. We classify processing memory architectures in two broader groups. The first one is what we call processing near memory architectures, which add logics near the memory chips to perform some computation, or processing using memory architectures, which uses the operating principles of the memory cells themselves for computation. And in this talk, we are going to mostly talk about processing using memory architectures. In particular, is realization using DRAM cells, which we call processing using DRAM. For us to understand how processing using DRAM architectures work, I need to give a little bit more background on what is the DRAM hierarchy, DRAM organization and operating principles. So DRAM is hierarchically organized as a series of components. In the top level, we have a DRAM mat, which is a 2D array of DRAM cells. Those DRAM cells are horizontally connected through word lines and vertically connected to bit lines. So the bit line shares a local sense amplifier, and the bit line shares a local row decoder. In the next level of the hierarchy, we have a DRAM subarray, which is composed of several DRAM mats. Those DRAM mats shares a row decoder, and a global word line spans across the different DRAM mats in the DRAM subarray. They also share a global sense amplifier, which moves data from the DRAM subarray to the I/O interface and eventually to the memory channel. In order to access DRAM, the memory controller issues two main commands to the DRAM chip. The first one is activate commands to a particular DRAM row. So upon receiving a DRAM activation command for a given DRAM row, the row decoder is going to assert one of the many D1 word lines across the many DRAM mats in the DRAM subarray, which enables the DRAM cells to be connected to the local bit line. This is going to generate a perturbation in the voltage level in the local bit line, depending on the charge stored inside the DRAM cell itself. Then the DRAM chip is going to sense, the local supply is going to sense this perturbation and amplify this voltage level to either a logic 1 or a logic 0 value. At the end of this process, the local amplifier stores the data, stores and elects the data for follow-up column accesses. Then the memory controller issues a column access, either a read or a write operation to the DRAM chip, which moves portions of the data that is stored in the local sense amplifier to the global sense amplifier and eventually to the memory channel. So prior works have shown that we can use these operating principles of the DRAM, these activate commands, to implement a series of processing-using-DRAM operations. So we're going to start very simple by implementing in-DRAM row copy operations. Let's say that we want to copy a source row inside the DRAM chip to a destination row without the intervention of the CPU doing this operation. So row clone shows that by issuing back-to-back activations to the DRAM chip, we can implement such operation. So the way that it works is by first activating the source DRAM row, which brings the source data into the local sense amplifier. And then we issue a second activation to the destination row, which is going to connect the DRAM cells in the destination row to the local sense amplifier, and hence the data is going to be copied from the local sense amplifier to the destination row. We can leverage a follow-up idea similar to that to implement in DRAM majority of 3 operations. So the main idea here is a little bit different. We are going to now activate 3 DRAM rows at the same time doing the computation. So let's say that we have 3 DRAM rows, source 1, source 2, and source 3, and we simultaneously activate all of the 3 DRAM rows at the same time. This is going to allow the cells in those 3 DRAM rows to be connected to the local sense amplifier into the local bit lines. And since the local sense amplifier is a differential circuit, this differential circuit is going to pull the voltage level to the majority of the voltage level stored in the 3 DRAM cells that were activated. In the example over here, we would have the majority of 1 in blue, 0 in yellow, and 1 in blue again, which is blue or 1. And the data is going to be stored in all of the 3 DRAM rows that were activated during the computation. So, okay, now we can do those in-DRAM row copies and in-DRAM majority operations by using those multiple row activation commands. But can we do something more interesting, like arithmetic operations? And the answer is yes. So this prior works from our group called MIMDRAM that provides a framework that can map different arithmetic operations to a series of in-DRAM row copy of majority primitive that implements arithmetic operations. I'm going to highlight here how this framework operates by implementing a in-DRAM addition operation. So let's say that we have a vector, 2 vectors, A and B. Each vector stores 1 bit with as many elements in this vector as DRAM colors in the DRAM subarray. Here, both vectors are going to store value 1. And we also have initialized carry in row, which store all zeros. So the first step of the MIMDRAM framework is to take a desired operation. Here I have a read carry header implemented Boolean gate, and translate these Boolean-based operations into a majority not inverted graph, which only uses the majority and not gates during the computation. Then in the second step, MIMDRAM traverse this majority inverted graph node by node, issuing triple row activations and in-DRAM row copy operations as stated by the circuit. So in the first example here, we implement the first majority node, which involves inputs A, B, and carry in by issuing triple row activations to such DRAM row. When we activate those 3 rows at the same time, you're going to have the majority of 1, 1, and 0, which is going to be 1, and this the output is going to be the carry out for the follow-up operation, and it's going to be stored in a carry out row. Then we move to the next majority gate, which involves row A, B, and carry in. And the majority of those cells are going to be the majority of 0, 1, and 0, which is going to be 0, and the data is going to be stored in a temporary row. Then we finally have the final majority gate, which involves the previous 2 computed majority gates and the input row A, which involves data values 1, 0, and 0, which is going to output 0. So in the end, we have the result of our MIMDRAM addition operation in the rows carry out and sum, which stores 1 and 0 respective. 1 and 0 is 2, which is the output of our initial MIMDRAM addition operation. So by operating DRAM in this way, SIMDRAM basically implements a very wide bit 0 SIMD engine inside the DRAM chip itself. And this SIMD engine is very wide because we have as many SIMD lengths as we have DRAM colors in your DRAM subarray. So in currently DDR4 chips, we have around 65,000 columns. So each one of those columns becomes a SIMD lane in this execution model. So before I move on to MIMDRAM itself, I want to just highlight that we have shown in your group that currently commodity of the shelf DRAM chips can implement a subset of those DRAM operations that I did describe here by violating DRAM timing parameters. So in this work that we present also in HPC 2024, we showed that commodity of the shelf DRAM chips can simultaneously activate up to 48 rows in 2 neighboring subarrays, can perform NOT operations with up to 32 output operands, and can perform up to 16 input AND, OR, and NOR operations. Of course, there is a reliability componenting of such operations, but it's just this work shows that we can have some significantly high success rate for several of those operations in commodity of the shelf DRAM chips as they stand today. So going back to the limitations of current processing using DRAM systems, we highlight in this work that prior processing using DRAM architectures that implement SIMD-like programming models often suffers from 3 sources of inefficiency due to the large and rigid DRAM access granularity. The first one is SIMD underutilization. Basically, since we have a very large SIMD width inside the DRAM subarray, which is dictated by the number of DRAM columns, what we have in the DRAM subarray. If the data parallelism within your application or across different applications is not a perfect multiple of the number of DRAM columns in the DRAM subarray, you're going to suffer from SIMD utilization when mapping your primitives to process using DRAM operation, which are going to lead to throughput and energy waste for many applications. Second, they have a limited computing support. So if you pay attention to the background that I just provide for in-DRAM row copy, in-DRAM Boolean operations, and in-DRAM arithmetic operations, all the time I'm taking 2 vectors and generating a 3rd vector as an output in what we call map operations. So if you want to implement something more complex, like an in-DRAM reduction operation, which you would take a vector and generate a scalar operand, you would require to implement interconnect networks that connects the different DRAM columns inside the DRAM subarray to support such primitives, which incurs non-trivial costs for the DRAM substrate. Third, they have those process DRAM systems have a challenging programming model because the way that we program such systems is with assembly-like programming APIs, which creates a burden for the programmers and limits the process using DRAM adoption. So in our paper, we have motivational data highlighting all of those 3 sources of inefficiency, but by the sake of time, I'm going to briefly summarize the problem and the goal that we have in this paper. So the problem that we are trying to solve here is that the large and rigid granularity of process-using-DRAM architectures limits the applicability of such systems for many different applications. And our goal is to design a flexible process-using-DRAM system that can overcome those three limitations. So to this end, we propose MIMDRAM. So the key idea of MIMDRAM is to use the DRAM's hierarchy organization to enable what we call fine-grained DRAM access. So when you access a DRAM row, even if after accessing a DRAM row, your column access is going to only target only portions of that DRAM row, the entire DRAM row is sensed and amplified by the local sense amplifiers during the DRAM activation command, which can cause energy waste for many applications. The reason of this happening is because the global word line inside the DRAM subarray is spanned across all of the DRAM mats inside the DRAM subarray during the DRAM row access. So to try to mitigate this energy waste that can be caused by what we call coarse-grained DRAM activation, prior works have proposed fine-grained DRAM architectures, which basically segments the global word line and allow one to access individual DRAM mats doing computation. So this idea is not new. This idea of fine-grained DRAM have been studied for energy-efficient DRAM systems over the past decade, and we have I'm going to highlight a paper that we have this year in TACO called Sector DRAM that built on those works and tried to design energy-efficient fine-grained DRAM access for many applications. But here we are going to use this concept of fine-grained DRAM for processing-using DRAM architectures, not only for regular DRAM accesses. So by employing such fine-grained DRAM architectures, we have three main benefits. So first, we can improve SIM utilization, because for a given process-using DRAM operation, we can activate only the given DRAM mats that have data that are going to be involved during this process-using DRAM operation. This creates another benefit, because for the remaining pieces of the main portions of the DRAM mats inside the DRAM subarray, which are not utilized during the given operation, we can target data-independent process-using DRAM instructions that can execute concurrently over those different DRAM mats inside the DRAM subarray. Hence, we can implement a new execution model, a multiple instruction, multiple data execution model inside a single DRAM subarray, where each DRAM mat implements a single instruction, multiple data execution model. The second benefit that fine-grained DRAM provides for process-using DRAM architectures is the implementation of in-DRAM reduction operations at low cost. Basically, by simple modifications to the DRAM peripheral circuitry, we can implement low-cost inter and intra-mat interconnect inside the DRAM subarray, which allow us to move pieces of data from one DRAM mat to another DRAM mat, or across different columns inside a single DRAM mat itself. And by using this interconnect, we can implement in-DRAM reduction operations. Finally, a nice feature that the DRAM mats have is that the number of columns, hence the number of SIMD lanes that we have inside the DRAM mat, is on par with the number of SIMD lanes that we have in modern processor ISA. So currently there are 4. We have around 512 different DRAM columns, which are going to be used as SIMD lanes in process-using DRAM engines, and hence we can leverage current programmer support to map those processor-based vector instructions to process-using DRAM vector instructions transparently from the programmer. So based on that, based on this key idea, we propose MIMDRAM, which is this hardware-software co-design process-using DRAM system that enables fine-grained process-using DRAM computation at low cost and low programming effort. So MIMDRAM is composed based on hardware and software components, which I'm going to very briefly highlight in the next slide. Start with the hardware components. So the first hardware components that we have in MIMDRAM is some simple modifications that we do to the peripheral circuit of the DRAM subarray to enable fine-grained DRAM computation and in DRAM reduction operations. For fine-grained DRAM activation, basically we design some isolation transistors and row decoder latch, which segments the global word line inside the DRAM subarray, enabling us to access different DRAM METs. Also we implement a MET selector logic inside the DRAM chip, which allow us to access the appropriate MET range for a given process using DRAM operation. We also provide simple modifications to the column access logic inside the DRAM subarray with an intermet interconnect, which allow us to move data from one DRAM MET to another DRAM MET at low cost. So on the CPU die, we implement a control unit, the memory controller, which allow us to schedule and orchestrate the execution of multiple processes using DRAM operation transparent from the programmer with simple logic. For more details of the control logic, I invite you to check our paper. So on the software side, we implement compiler support, which has a goal of extract SIMD parallelism from application and schedule process using DRAM instructions transparent from the user while maximizing the utilization of our underlying process using DRAM substrates. Based on that, we implement 3 LLVM passes targeting process using DRAM execution. So the first pass is has a goal of code identification. Basically, here we took LLVM loop auto vectorization engine and we implement some simple modifications to that so that we can generate process using DRAM instructions while maximizing the SIMD parallelism across a given auto-vectorizable loop. The second LLVM pass is responsible for code scheduling and data mapping. So basically, our goal here was to identify which of those previously generated auto-vectorized process using DRAM instructions are data independent and can be executed in different DRAM METs concurrently doing computation, and which instructions are data dependent and need to execute inside the same DRAM METs to avoid unnecessary data movement inside the DRAM subarray during the computation. And we, based on that, we implement some, we annotate the code with some metadata that is going to be used for the control unit later on during the execution to trigger the process using DRAM computation in the appropriate DRAM METs during the computation. Finally, the final pass is responsible for code generation, and basically here we modify the 8086 backend to generate new process using DRAM instructions for process using DRAM operations. So we also describe in our paper the system support that we implement in MIMDRAM, which is required for the compilation steps to work correctly, and those include instruction set architecture, execution, data transposition, data coherence, address translation, data location and alignment routines for process using DRAM architectures, and some metadata translation. And for all of that, I invite you to check our paper for more details. So I'm going to head into the evaluation of MIMDRAM. So we implement MIMDRAM using the Gen 5 simulator, and we compare it with real-world CPU and GPU processor-centric system, a prior process using DRAM architectures, SIMDRAM MIMDRAM, and a processing near DRAM architecture called Funko. So we use 12 workloads from 4 benchmark suites in your evaluation, and we combine those workloads into 495 different multi-program application mixes for where we can use 2 main different analyses. The first one is a single-level application analysis, which allows MIMDRAM to leverage inter-application data parallelism. So we can only leverage the parallelism inside across the different loops or the instructions inside the loop for process using DRAM execution, where in the multi-program workload analysis, we can leverage inter-application data parallelism for process using DRAM execution. I'm going to highlight some of our results in your paper. We start with a single application analysis. So here in this plot, we have in the x-axis the 12 different applications that we evaluate in your systems. And in the y-axis, we have the CPU normalized performance per watt for the CPU, SIM-DRAM, and MIMDRAM architecture. So the values, again, are normalized based on the CPU system. So we basically make the observation that compared to the CPU, GPU, SIM-DRAM, MIMDRAM provides significant improvement in terms of energy efficiency, because basically SIM-DRAM avoids SIM underutilization and fully utilize the DRAM METs inside the DRAM subarray for processing using DRAM computation. When you analyze the multi-program workloads, we see that MIMDRAM compared to SIM-DRAM using 1 bank, 2 banks, 4 banks, and 8 banks for computation significantly improve system throughput. Again, because here we are fully utilize the different DRAM METs inside the DRAM subarray, which provides higher throughput than using multiple DRAM banks that cannot be fully utilized for computation. In the paper, we have many more evaluation results, including MIMDRAM results with subarray and bank level parallelism, comparison to Drizzle and Funko from multi-program workloads, MIMDRAM SIM utilization versus SIM-DRAM, and the area analysis of MIMDRAM. And again, for all of that, I invite you to check our paper. So I'm going to briefly conclude. So in this paper, we introduce MIMDRAM, which is a hardware-software co-design process using DRAM system, which leverages the key idea of fine-grained DRAM activation for processing using DRAM operations in both hardware and software. On the hardware side, we propose some simple modifications to the DRAM peripheral logic, which enable us to concurrently execute different in-DRAM operations inside a single DRAM subarray, and to move data across different DRAM METs inside a different DRAM subarray, which enable us to implement in-DRAM reduction operations. On the software side, we implement compiler and operating system support, which enables us to generate and map instructions for high-level C code down to the process using DRAM substrate transparently from the user. So we sensibly evaluate SIM-DRAM, and we saw that it can significantly outperform processor-centric and memory-centric architectures, while we carry a small area close to the DRAM chip and the CPU die. So this concludes the MIMDRAM talk. I'm going to do some quick marketing about our processing using DRAM processing memory class that we have been conducting here in ETH Zurich. So these are semester-long lectures that we give every Wednesday on processing in-memory architectures, covering processing using DRAM, processing memory, processing using memory architectures, and all of our lectures are available online and live stream on YouTube. We also have been conducting some tutorials on process memory architectures. We just gave a tutorial in Micro this year in Austin, which was quite well attended, and the materials are all available online. And we have follow-up to process memory tutorials in PPOP next year in Las Vegas in March. And we have the very first memory-centric computer system workshop. This is not a tutorial, it's a workshop that's going to happen in ASCLOS in 2025, late March, where we are going to invite the community to submit five-page long work on progress papers, and the call for paper is going to be available soon. You should expect a deadline for paper submission in late January. So this concludes, I forgot to talk about our PIM book chapter. So if you don't want to listen to me talking about process memory for many hours, you can just read or develop some process memory architectures in your PIM book chapter, which we are going to release a new version in the beginning of next year as well. So this finally concludes my talk. I'll be glad to take any questions, and thank you very much for listening.
All right, thank you very much, Geraldo. Let me stop the recording.